Successive nuclear decay is when a radioactive nuclei decays into a daughter nuclei, which is also radioactive, that further decays into another stable daughter nuclei. Now, many of you who may have studied nuclear physics would have probably studied the first process when a radioactive nuclei decays into a stable daughter nuclei. You must have studied the radioactive decay law and the various expressions involved. But what if the daughter nuclei is not stable? What if it is also radioactive and decays further into something else? That is the problem that I want to study today. I want to find out the various decay expressions associated with some kind of a radioactive nuclei A, which decays into B, which further decays into C, and the decay constants from A to B is lambda A, and from B to C is lambda B. In that kind of a scenario, what would be the composition of this kind of a substance at any given point in time? What is going to be the ratio of the various nuclei at any given point in time? That is what I want to derive in this particular video. And once I do that, I also want to obtain some additional information. I will try to find out the time period at which the intermediate radioactive nuclei is maximum. I will also describe what is called transient equilibrium and secular equilibrium. So once you watch this whole video, you should be able to describe in very much detail the process of a successive nuclear decay. And if you want to take this further, if you want to go from A to B to C to further D, you can follow this same method and perform the calculations to obtain something more. All right, so let us start. I have given you the graphical representation here, the results here, but I want to derive the results myself. Okay, so if I derive the results myself, I want to keep this graph on the side for a while so that I can focus on my own calculations. Okay, so if I focus on my own calculations, the graph, the results are on the side. I will derive it myself first. All right. Okay, so you must be familiar with the radioactive decay law. Whenever some sort of a radioactive molecule decays, then the radioactive decay law simply tells us what is the rate at which a certain radioactive nuclei is decaying. And experimentally speaking, it is directly proportional to the total number of radioactive nuclei present at that given point in time. So if we focus on the decay from A to B, in that kind of a situation, the rate at which A decays with respect to time is simply equal to minus lambda A and A. I think most of the symbols here are kind of obvious, that we have these radioactive nuclei A, we have this radioactive nuclei B, and we have the final stable radioactive nuclei C. Okay, and lambda A and lambda B are the decay constants from A to B and B to C respectively. Initially, there is no B and C in the original composition, there is only A. And the total number of radioactive nuclei corresponding to A initially at time t is equal to 0 is n naught. So based on this, we are going to do our various calculations. So the radioactive decay from A to B, the law is given as dNA upon dt is minus lambda A and A. So this is the rate at which A decays into B. It is negative because A is decreasing with time. So it is directly proportional to the total number of A radioactive nuclei, and lambda A decay constant is simply the proportionality constant. Now, if we look at the decay from B to C, now this is the rate at which the radioactive nuclei B decays into C, which is equal to minus lambda B and B. So it is clear that the rate at which a certain radioactive nuclei decays is directly proportional to the amount of radioactive nuclei present at a given point in time. Now, if I want to figure out an answer to the question that what are these intermediate, what is the composition of the intermediate nuclei at any given point in time, I need to understand that the rate at which A decays into B is also the rate at which B is being formed, right? The rate at which A decays into B is also the rate at which B is being formed. And the rate at which B decays into C is the rate at which B is decaying. So therefore, the net rate of formation of B is given by a combination of both. So you have to understand that this expression is essentially creation of NB. Okay, this basically gives us an idea about the creation or the formation of B. So therefore, the rate at which, if I can write it in a fashion, dNB upon dt, which represents the net rate at which B is decaying as well as forming, then it is simply equal to nothing but lambda A and A minus lambda B and B. So keep in mind that this is the rate of formation of B and this is the rate of decay of B into C. So I want to solve this equation first. If I can solve this, then my calculations would follow automatically. And keep in mind that the rate at which the decay of A happens automatically leads to a very simple equation. I think most of you are already familiar with it. Na is equal to the initial number of nuclei e to the power minus lambda at. We'll also be using this expression later on. So this is simply the radioactive decay law for the decay of A to B. Now I want to find out the decay of B at any given point in time. Okay, so to do that, I simply need to solve this particular equation. So dNB upon dt plus lambda B and B is equal to lambda A and A. So the lambdas are the decay constants and capital N is essentially the total number of radioactive nuclei at any given point in time. To solve this, I will simply multiply this entire equation with e to the power lambda bt, so lambda A and A e to the power lambda bt. Okay, so if I do this, things become a bit simpler and it helps us in solving this equation, because if you look at the left hand side, the left hand side can simply be written as the time derivative of the product of NB and e to the power lambda bt. If you look at it carefully, the first expression is e to the power lambda bt times dNB upon dt, and the second expression is quite simply put NB lambda b e to the power lambda bt. Okay, so essentially you end up getting this expression from here. That's why I've written it to substitute the LHS. And the RHS, since Na is equal to N naught e to the power minus lambda at, I'll just write that here, N naught e to the power minus lambda at, and here we have e to the power lambda bt. So I've simply substituted Na with this particular expression. Okay, now it will become much easier to actually solve this particular expression. Okay, because here what we can do is I can simply take d and b e to the power lambda bt is equal to lambda a and not e to the power, here I can write lambda b minus lambda a t, and I integrate with respect to t on the right hand side. Okay, and integrate here with respect to d and b e to the power lambda bt. Okay, so if I plug in the integration limits, so for the number of radioactive particles b, it goes from 0 to nb, and time goes from 0 to, let's suppose, just t. This is easy to solve. This is simply nb e to the power lambda bt, which is equal to lambda a upon n naught lambda b minus lambda a e to the power lambda b minus lambda a, and the limits of 0 and t. And this will give us a very simple expression, which is nb e to the power lambda bt is equal to lambda a and naught upon lambda b minus lambda a. And here I will have e to the power lambda b minus lambda a t minus 1. All right. So we have almost obtained the final expression. I just need to take this expression to the right. Okay. Here, the exponential term, I want to take it to the right so that finally I am only left with nb in the left hand side. So if I take this to the right, then this expression simply becomes lambda a and not lambda b minus lambda a. And then here I have e to the power. So if I take e to the power lambda bt to the right, it just ends up becoming e to the power minus 1 e to the power minus lambda bt. So then what happens here is that the e to the power minus lambda bt gets cancelled with the first term, and I am just left with this expression essentially. So I will have minus lambda a t minus e to the power minus lambda bt. That's it. All right. This is the number of radioactive nuclei, the intermediate nuclei at any given point in time. Okay. This is the number of intermediate radioactive nuclei at any given point in time. And the number of radioactive nuclei of the original parent nuclei, this is this one. So this is, let's suppose, the parent nuclei at any given point in time. Clearly it follows the radioactive decay law, so it exponentially decays, right? The second expression is a little bit complex because not only the intermediate daughter nuclei is being formed, but it is also decaying further. So as a combination of both of these two things, this is the expression for the intermediate radioactive nuclei at any given point in time. Now I can further use this to obtain the radioactive nuclei C at any given point in time. So if you look at this expression here, the formation of the radioactive nuclei C is simply given by this particular expression, right? This particular expression, because the rate at which B is decaying into C is the rate at which C is forming. So this is nothing but dNc upon dt. All right. So if I apply this expression here, so Nc is essentially equal to, so rate of formation of C, and here I am assuming that C is a stable nuclei. If you want to assume that C further decays into something like D, then you have to keep on doing the calculations. But I'm going to assume that C is a stable nuclei. So rate of formation of C. So the rate of formation of C, dNc upon dt, is quite simply put equal to lambda bnb. That's it. It's simply going to be equal to lambda b and b, where nb is what we have just now obtained, and I want to substitute that here to finally get the third expression. So this should be dNc is equal to lambda a, lambda b, and naught upon lambda b minus lambda a, and then integrate e to the power minus lambda at minus e to the power minus lambda bt. Okay. If I do that with respect to time, and here The integration is from 0 to nc, and this is from 0 to t. If I do this, I should come up with an expression for the last stable nuclei. So left hand side, we have nc is basically equal to okay, what is this? This is e to the power minus lambda at upon minus lambda a minus e to the power minus lambda bt upon lambda b plus integrated from 0 to t. If I solve this further, it will give me, let me see, minus e to the power minus lambda at upon lambda a minus plus e to the power 0 is 1 and here minus it should be 1 upon lambda a, right? This should be 1 upon lambda a and this should be 1 upon lambda b. Okay, we are almost there. Just one more expression remaining. So nc at any given point in time is equal to how can we write this? So na and nb will get cancelled and I will be left with n naught lambda b minus lambda a, and I will be left with, what should I have? Lambda a lambda b will get cancelled. This is going to be minus lambda b e to the power minus lambda at plus lambda b plus lambda a e to the power minus lambda bt minus lambda a. If I organize all of this into one expression, finally it should look something like n naught upon lambda 2 minus lambda 1 and here we have, sorry, lambda b minus lambda a minus lambda a, and this becomes, if I take lambda b common, this becomes 1 minus e to the power minus lambda at, and if I take lambda a common, this becomes 1 minus e to the power minus lambda bt. All right, there it is. This is the final expression for the stable daughter nuclei. Now they may look a little bit complicated because ultimately it is not a very simple radioactive decay. On one hand, a radioactive decay is happening that is creating it, and on the other hand, there are multiple radioactive decays that has happened earlier that decides what is the total number of radioactive nuclei C at any given point in time. But if I combine all these expressions, so on one hand, I have this expression. Let me just copy paste it. I have this expression, which is the number of radioactive decay, or sorry, number of radioactive parent particles at any given point in time. This is the first expression. And the second expression is this one, number of intermediate radioactive nuclei at any given point in time. Okay. And finally, we have this expression, which is the number of final stable radioactive nuclei at any given point in time. Just a moment. There we have it. These three important expressions. So if you want, you can plot them in some kind of a graphical editor or something. And if you plot them, you should get something that looks like this. Just give me a moment. So this is the first expression. This is the second expression. And this is the third expression. If you plot all of this, you will get this graph that I have obtained earlier. Okay, do you remember this graph? This one. I had already drawn this graph just so that I don't have to draw it again, because when you draw a graph, you are very likely to make mistakes. And just a moment. Yeah, there it is. So you see what's happening. You can clearly see that initially there was only radioactive nuclei A in the sample, but that starts decaying exponentially. And suddenly there is an influx of radioactive nuclei B, which increases because it is being formed because of the decay of A. But then the B also starts decaying further, and slowly, slowly C takes over. And because C is stable, ultimately the entire composition will be filled with C. Okay. So these are the interesting expressions for the radioactive sample containing the original parent nuclei, the intermediate radioactive nuclei, and the final stable daughter nuclei. Now, if you want, we can do further calculations here. For example, I can also calculate what is the time period that it takes for the intermediate nuclei to reach its maximum sort of amount. So what is the time at which the intermediate nuclei is at maximum? Okay, so that is something. These are some questions that may arise sometimes. Okay, so let me write down the question. After how much time and let me say this is TB, is NB maximum? Okay, sometimes they may ask you a question like this. In that kind of a situation, so this is TB, it is not a difficult problem. It is actually very easy, because in mathematics, any kind of a function that has a maxima can be found out by making its derivative with respect to the variable equal to 0. That's it. So because I already have an expression for the number of B molecules at any given point in time, I just need to take its derivative and make it equal to 0. So dNB upon dt is equal to 0. That is all I need to do. So the time derivative of NB, where NB is equal to this expression, lambda A N naught upon lambda B minus lambda A, and you have e to the power minus lambda A T minus e to the power minus lambda B T is equal to 0. Let me just make sure that the expressions that I've obtained are actually correct by comparing it with my earlier notes. Yeah, this is correct. I think this is correct. All right. So now if I perform our calculations for the second question, which is what is the time at which the intermediate nuclei is maximum, for that I just need to do a derivative of this. Okay. So this will become minus lambda A e to the power minus lambda A T minus minus plus lambda B e to the power minus lambda B T. The constant goes to the right hand side, becomes 0, right? So all we are left with is whatever expression is within the brackets. So that simply becomes lambda A e to the power minus lambda A T, which is equal to lambda B e to the power minus lambda B T. Now, if I take the one of the exponentials to the other side as in the sort of denominator, then this is simply going to become e to the power, let's suppose, if I take a to the other side, so in that case, this is going to become lambda A upon lambda B So this is going to be equal to e to the power lambda a minus lambda b. Okay, all right. This is what it becomes. So what is T here? T is TB, right? At T is equal to TB. So I can just substitute TB here. So this is simply nothing but log of lambda A upon lambda B is equal to lambda A minus lambda B TB. Okay. So finally, we have our result, which is the time period at which the intermediate radioactive nuclei reaches its maximum is equal to 1 upon lambda A minus lambda B log of lambda A upon lambda B. That's it. So that means even theoretically, the intermediate daughter nuclei will approach a maxima, and finally it would sort of start decreasing, because finally the stable daughter nuclei takes over the entire process. Now, before I wrap up this video, I also wanted to mention two more things. If you're studying this particular topic, it might be helpful. So one is what is called secular equilibrium, and the other is what is called transient equilibrium. So remember when I mentioned that the rate at which the intermediate daughter nuclei is being formed is a result of two things. It is a result of the formation of the intermediate radioactive nuclei, as well as the decay of the intermediate radioactive nuclei. So what if the rate at which it is being formed and the rate at which it is decaying is exactly equal? What if the rate at which this intermediate nuclei is being formed is exactly equal to the rate at which the intermediate nuclei is decaying? And in that kind of a situation, the number of intermediate nuclei will remain a constant, right? So that is called a secular equilibrium. Okay. If you're studying this topic, it would give you a completion of all the things necessary. Okay, so secular equilibrium. So the secular equilibrium is when the rate at which the intermediate radioactive nuclei is being formed and is decaying is exactly equal to 0. That means this expression that we had, this is equal to 0. Okay, the rate at which it is being formed and the rate at which it is decaying is exactly equal to 0. So lambda A and A minus lambda B and B is exactly equal to 0. Is exactly equal to 0, which gives us a very simple expression: lambda A and A is equal to lambda B and B, or an A upon, so we know that the radioactive decay constant is inversely proportional to its half-life. It's inversely proportional to its half-life. So if you want to make a comparison with the half-life, you can also write TA here, which is the half-life of A, and NB upon TB here, which is the half-life of B. Okay, so Na upon Ta is equal to Nb upon Tb. So in a sense, the ratio of the number of particles A upon its half-life is equal to the ratio of the number of particles B upon its half-life. Okay, so this is called secular equilibrium. There is also one more concept called transient equilibrium. So transient equilibrium is what happens when there is a very strong difference between the radioactive decay constants of A and B. So for example, if the decay of B, the decay constant of B is extremely large compared to the decay constant of A. what happens then? You see, B cannot decay unless it is being formed, right? For the intermediate daughter nuclei to decay further, it has to be formed in the first place. So what if the original parent nuclei is decaying very slowly, but the intermediate daughter nuclei decays very fast? What happens in that case? So the intermediate daughter nuclei has a decay constant which is very high, so it decays very fast, but the parent nuclei has a decay constant which is very small. That means the rate of formation of B is very, very less. In that kind of a situation, if I again take a look at this particular expression, okay, this is our NB, right? Let's just copy paste it here. So this is NB. This is NB. What happens to this? So if lambda B is very, very large compared to lambda A, in that kind of a situation, this expression approximates to 0. Okay, if you make a comparison between lambda A and lambda B, because we have exponential to the power lambda, to the power minus lambda, so exponential to the power minus lambda B will tend to 0. Or I can approximate this expression in that particular manner for this particular limit. So then NB is approximately equal to, what is this? This is N naught lambda A upon lambda B minus lambda A e to the power minus lambda AT. Do you see what's happening? So the daughter nuclei or the intermediate daughter nuclei is decaying with the half-life of the parent nuclei. And B is decaying with the half-life of the parent nuclei, essentially. That's what's happening. Okay, if I combine this with Na is equal to N naught e to the power minus lambda AT, it simply means that NB is approximately equal to lambda A upon lambda B minus lambda A. Na. Okay, so the daughter nuclei is essentially decaying with the half-life of the parent nuclei. This is because the daughter nuclei decays very fast, but it can only decay if it is actually formed in the first place, and the formation rate is very, very less. All right. So if you're studying this particular topic, I hope you have understood all these things, and hope that this will help you in your studies. Successive nuclear disintegration process. Very interesting topic. If you want, you can do further the disintegrations. You can do a similar calculation to find D, E, and further kind of a series. That is all for today. I'm Divya Jyotidas. Thank you so much, guys. If you guys are interested, then you can also check out our various courses. So we have courses on Physics IIT JAM and csir-net Physics. And we launch recorded as well as live batches every 6 months. So if you're interested in Physics IIT JAM or csir-net or Gate Physics, you will find those exclusive dedicated courses in our Elevate Classes platform. You can download our app. You can be one of our students. You can get selected to like some of the great institutes of our country. We have an upcoming batch in December for net physics. If you're interested, download the app, check out the course. If you're interested, join us, start your preparation. That is all for today. Thank you so much. I'll see you next time. Bye-bye.